We've discussed how cut elimination works for individual cuts of various kinds. What's left is putting that together to eliminate all cuts in a deduction. The main point is that we can reduce the cut rank of a deduction. That is, theorem. If z infinity deduces gamma using cuts of rank less than c plus 1, then z infinity still deduces gamma using cuts of rank less than c. So we can eliminate all the cuts of rank exactly c. This process will cost us a lot of height. If the original deduction had bounds alpha comma k, the new one has bounds omega to the alpha, h omega to the alpha of k. The proof, of course, is by induction on alpha, with cases depending on the last step of the deduction. The main case, naturally, is a cut of rank c. That means there's a formula phi with rank exactly c, so that z infinity deduces both gamma phi and gamma naught phi, with bounds beta and gamma both less than alpha. Phi and naught phi are symmetric here. We could instead talk about naught phi and not phi. Recall that for each kind of pair of formulas, we have an inversion lemma. So one side of the cut is the side we invert. And I'm going to assume that phi is the invertible formula, which means phi is either a false atomic formula, a conjunction, or a for-all formula, and not phi will be its negation, either a true atomic formula, a disjunction, or an exists formula. By the inductive hypothesis applied to both sides, z infinity deduces gamma phi and gamma naught phi, with bounds omega to the beta and omega to the gamma, and cuts of rank less than c. And then we go through cases for what the cut formula could be. If phi is atomic, phi is false, and by the atomic inversion lemma, z infinity also deduces just gamma, with bounds omega to the beta, and we can use weakening to get the right bounds. If phi is psi 0 and psi 1, then, by the inversion lemma for AND formulas, we have deductions of gamma psi 0 and gamma psi 1, with bounds omega to the beta, h omega to the beta of k, and then we use our reduction lemma. We have a deduction of not psi 0 or not psi 1, we have a deduction of psi 0, we have a deduction of psi 1, so we have a deduction of just gamma, with height omega to the beta plus omega to the gamma. And since beta and gamma are both less than alpha, omega to the beta plus omega to the gamma is less than omega to the alpha, so we can use weakening to get the bounds we need. Finally, if phi is for all xi, we can use inversion for all formulas. For each n, we have a deduction of gamma comma psi of n, and again our reduction lemma applies. We have a deduction of gamma with bounds omega to the beta plus omega to the gamma, comma h omega to the beta plus omega of h omega to the gamma of k. The way we defined the h functions, and remember tau of beta and tau of gamma must be less than k, because these came from the previous steps of a deduction with bounds alpha comma k. So the numeric bound is less than h omega to the alpha of k. So we do get a deduction of gamma with exactly the bounds we promised and with all cuts of rank less than c. That's the main case, the case where we actually eliminate a cut rule. For all the other steps, as you might expect, we just apply the inductive hypothesis. Just to see one example. If the last step is an OR introduction, so we deduce gamma comma phi or psi from gamma comma phi, the bounds of the previous deduction are some beta less than alpha with tau of beta less than k, and then the inductive hypothesis gives us a deduction of gamma comma phi with cut rank less than c, and height omega to the beta. And then OR introduction gives us the deduction we want of gamma comma phi or psi. One last time, if we're being extremely formal, we would have to go through and verify the cases for every single deduction rule, and as always, we won't do that. The other cases are all very similar to the OR introduction rule. And that's the end of that lemma. That's how we reduce the rank of the cuts by 1. Let's add a definition so we can iterate this. We'll write omega to the alpha sub c to mean alpha raised to the omega power c times. Formally, we define omega to the alpha sub c to be alpha, and omega to the alpha sub c plus 1 to be omega to the omega to the alpha sub c. So omega to the alpha sub 1 is just omega to the alpha. Omega to the alpha sub 2 is omega to the omega to the alpha, etc. Then, if z infinity deduces gamma with bounds alpha comma k and cuts of rank less than c, also z infinity deduces gamma with bounds omega to the alpha sub c, comma h omega to the alpha sub c of h omega to the alpha sub c minus 1 of ... So some number m. We don't really care about the exact number. We just care omega to the alpha, some natural number m, and cut rank 0. No cuts at all. If we have a deduction of gamma with height alpha and a bound c on the rank of cuts, we have a cut-free deduction. We now have all the pieces we need, so let's recall how this all fits together to give us our main argument. Theorem. Goodstein's theorem cannot be proven from the axioms of PA+. Proof. Suppose we could prove Goodstein's theorem from the axioms of PA+. Then we could prove it in z infinity with bounds alpha k, where alpha is less than epsilon 0, and with a bound c on the ranks of cuts. By the cut-elimination theorem, we would have a cut-free proof of Goodstein's theorem with bounds omega to the alpha sub c comma n. When alpha is less than epsilon 0, omega to the alpha sub c is also less than epsilon 0. So this contradicts what we proved earlier. There can't be a deduction of Goodstein's theorem with bounds less than epsilon 0. So we can't deduce Goodstein's theorem in z infinity. And that's it. We're done. That's the complete proof. We had to work pretty hard for that. In particular, we needed to investigate the structure of deductions in P&O arithmetic very carefully to be able to derive that. And as you might hope, we can hope to get more out of all this cut-elimination machinery than just this one result. So in the final video in the series, I'll just wrap up by mentioning a couple of the directions that these ideas get used in modern proof theory.